Hello everyone, this is Vasant, a nine-pointer at IIT Bombay from the Department of Civil Engineering. In this video, we are going to study about pure bending with axial load. So in previous lectures, we studied about pure bending. Only pure bending means only one type of loading with bending moment constant at every cross section. And we analyzed that one. Now we are going to add one more loading to that is axial load. Why this type of topics is important? If you consider any civil engineering structure, at a time there will be variety of loadings, means it will be subjected to multiple loadings at a time. So the effect of that loadings will be combined effect of these all different types of loadings, right? At first, for simplicity, we will consider the effects of individual loadings. Now by using principle of superposition, finally we need to know about how will be the overall effect. So this is important for designing the structural elements. So this topic is important for designing the structural elements. Okay. So now we are considering only two different types of loads. One is pure bending one, and another is axial load. So we can say that by principle of superposition, it consists of pure axial one and one as pure bending one. If you sum those two, you will get the combined effect of those two, right? So due to pure axial one, if it is passing through this, suppose this is centroid of the cross section. See, we already discussed about this in axial loading. We said that for uniform stress distribution due to axial point load, concentrated point load, the line of action of that point load should pass through the centroid of the cross section. So this should be centroid of the cross section. Okay. So we will get uniform stress distribution sigma that will be given by P divided by A, right? Now another is pure bending, means stresses developed because of the pure bending moment M. So for that we know that sigma bending, this is sigma normal axial. So sigma bending will be given by My divided by I, that is actually minus, right? So sum of these two will be the combined effect of this bending moment and axial force P, right? So that can be given as sigma combined will be is equals to sigma A plus sigma B, right? So this is P by A and this is minus My by I. So this is combined stresses. See, for this one, for only pure bending, see what is neutral axis? Neutral axis is the position where the stress is zero. That means the strain is zero, means there is no elongation of that line. Okay. So that will pass through the centroid. So this will be neutral axis. But after these two effects, the actual neutral axis is somewhere else. So there can be a neutral axis, there can't be a neutral axis. That will depend on the these P by A values and My by I. So we need to get for neutral axis, sigma C should be is equal to 0, means P by A should be is equal to My divided by I. From that we can get Y of neutral axis. Okay. So see, if this can happen, we can get the neutral axis position Y from the neutral axis for pure bending case. From this the distance is Y, right? So if you get Y is equal to some distance, see this is the centroid. So this is neutral axis for pure bending case, but for combined effect the neutral axis at position Y. Okay, this is Y1. So this can be there or not there. That will depend on the magnitudes. Of the pure axial stresses and magnitudes of the pure bending stresses. Okay, so that can look like something like this and something like this. Okay, it can have compressive stresses also. I hope you understood the combined effect of pure bending plus axial load that can be solved using superposition. So see, don't worry about the sign conventions here also. first calculate the pure axial stresses, that is P by A from the intuition. If the load is away from the cross section, we can say that that is tensile. And we know that if there is positive bending moment, then we know that upper section may the bending moment, sorry, the bending stresses will be compressive, means negative. Lower section may the bending stresses will be positive. So from that intuition, you can put the sign conventions and solve the sigma, overall sigma at any position. Okay. So let us take one example to understand this, how we can identify the situation is a case of pure bending plus axial load. So this is the case. See, this is a link. Here the forces, compressive forces are applied. Compressive force P equal and opposite axial load is applied. So you need to understand whether it is this case or not. And see, if you cross sectional view is given and the P is applied over here, it is not applied at the centroid. It is not applied at the centroid. So we can say that we can transfer this P to this over here, and we can say the bending moment will be like this. That will be P into D, right? So this case will be at centroid, it will be P, and it will be negative movement. It is not positive because the curvature will look like this. Okay, so that P is PD. So why we are transferring it to centroid? Because we already said if the axial load is passing through the line of action of the axial force is passing through the centroid, then we can assume the stress distribution due to axial load is uniform. So see, because if you directly need to do axial stress distribution because of this load, that is statically indeterminate, right? So if you move the load to centroid, then we can find out with two cases. One is pure bending case because of this PD. So because of PD, pure bending, and because of P at centroid, pure axial with stress distribution, with uniform stress distribution. This is important because if it is not uniform, then it is statically indeterminate. We can't find it, okay, using these general equilibrium equations. So from this we can get that sigma axial will be is equals to minus P by A, right? We can calculate the area of this T section, right? And sigma bending stresses will be given by minus My by I. And this M is negative. If we want to put sign with sign conventions, then it will be PD into Y divided by I. Okay. This is I of T section. About neutral axis of pure bending. Okay. For that it will pass through the centroid. Okay. See, for pure bending case, the neutral axis will pass through the centroid. So this will be neutral axis for pure bending. But the actual neutral axis is for combined effect, right? So for neutral axis, we can write sigma axial plus sigma bending is equals to 0. So we can write minus P by A plus PDY by I will be is equals to 0. So we can get PDY by I will be is equals to P by A. This P gets cancelled. We get Y is equals to I divided by AD. Okay. So see, this Y is distance from centroid. Why? See, while you are writing sigma bending, this Y is distance from the centroid, means distance from the neutral axis of the pure bending. So that is the Y of neutral axis from centroid. So the pure bending plus axial load case can be obtained from eccentric axial loading, right? This is eccentric axial load, that is at a distance d from the centroid. So I hope you understood this concept. With this, we end this lecture. If you like this lecture, do subscribe to our channel 9 pointer. Thank you.